We now start module 7 of chapter 5, and we will talk on unitary and orthogonal operators. We will see that they are very rich in geometry. We will first learn their characterization, and then later on we will focus on orthogonal operators on the Euclidean spaces and see some of the very special ones like reflection and rotation operators, which are in fact in this category. Let us start. Let V be a finite dimensional inner product space over F. A linear operator T on V is said to be unitary if the field is the field of complex numbers and norm of Tx is equal to norm of x for all x in V. And the operator T on V is said to be orthogonal if the base field is the field of real numbers and norm of Tx is equal to norm of x for all x in V. If V is infinite dimensional vector space, then we usually call such norm preserving operators isometry. If we also have surjectivity, then we call them unitary or orthogonal operators depending on whether the field F is C or R. So, examples: rotation and reflection operators on R2. These are very important examples of orthogonal operators on the inner product space R2 with the usual inner product. These operators will appear once again when we study the geometry of unitary and orthogonal operators in detail. Example: let V denote the collection of all continuous complex valued function on the closed and bounded interval 0 to 2 pi. We know that it is an infinite dimensional inner product space over the complex field. Let us define T from V to V as T of F is equal to GF for a fixed G in V with mod of GT is equal to 1 for all T in 0 to pi. Then norm of TF square is norm of GF square, which by definition is 1 over 2 pi integral 0 to 2 pi GTFT times GTFT bar dt, and that is equal to norm of F square since mod of GT is 1 for all T in between 0 and 2 pi. Therefore, T is unitary. Note that V is an infinite dimensional inner product space and T is norm preserving, and also T is onto. Theorem: let V be a finite dimensional inner product space over F and T a linear operator on V. Then the following statements are equivalent. Statement 1: T star equal to T star T is equal to I. 2: inner product Tx Ty is equal to inner product Xy for all Xy in V. 3: if B is equal to set containing V1, V2, Vn is an orthonormal basis for V, then the set containing TV1, TV2 and so on Tvn is an orthonormal basis for V. In other words, T maps an orthonormal basis to another orthonormal basis. Statement 4: there exists an orthonormal basis B for V such that the set of all TV such that V belongs to B is an orthonormal basis for V. And 5 says that norm of Tx is equal to norm of x for all x in V. So, you can see that if we prove the equivalence of all these statements, then any one of these can be used as a definition of a unitary operator. Proof: 1 implies 2, inner product x comma y is equal to inner product t star t x comma y, and that is equal to inner product t x comma t y for every x y in V. This shows that T preserves the inner product on the inner product space V. 2 implies 3, inner product T Vi T Vj is equal to inner product Vi Vj, and that is equal to 1 or 0 depending on whether I is equal to j or I is not equal to j, since B, that is set consisting of V1, V2, Vn, is orthonormal. 3 implies 4 is obvious. 4 implies 5. Let x be equal to summation I equal to 1 to n ai vi for ai in the base field F. Then norm of x square is summation ai vi comma summation aj vj inner product, and that is equal to double summation I is equal to 1 to n, j is equal to 1 to n ai aj bar inner product vi vj, which is the same as summation mod of ai square for I equal to 1 to n. Again, because the set B consisting of V1, V2, Vn is orthonormal. Therefore, all the Vi, Vj's become 0 if I is not equal to j, and the only ones that survive are the inner product Vi, Vi's, but that is 1, and then we have ai, ai bar, and that gives rise to this mod of ai square. Similarly, by the same technique applied to Tx, we obtain norm of Tx square is equal to summation I equal to 1 to n mod of ai square, and therefore, norm of Tx is equal to norm of x. Finally, 5 implies 1. For any x in V, we have inner product x x is equal to norm of x square, and that is equal to norm of Tx square, and that is equal to inner product Tx Tx, and that is the same as inner product x comma T star Tx. Therefore, inner product x comma I minus T star Tx is 0 for all x in V. Let S denote I minus T star T. Then else is self-adjoint, and inner product x comma Sx is 0 for all x in V. Let B dash be an orthonormal basis for V consisting of eigenvectors of S. That is because S is self-adjoint, and therefore, we do have one orthonormal basis for V consisting of eigenvectors because it is diagonalizable. Let lambda be a scalar which is an eigenvalue of S. Then there exists an eigenvector V in B dash such that SV is equal to lambda V, and we have that inner product VSV which is 0, and it is equal to inner product V comma lambda V, that is because SV is equal to lambda V, and that is equal to lambda bar inner product V comma V. This shows therefore lambda bar is 0, and hence S is the 0 operator. Therefore, we get T star T is equal to I. This finishes the proof because we have showed that all the statements are equivalent. Now, definition: an n cross n matrix A is said to be orthogonal if A transpose is equal to A transpose A is equal to the n cross n identity matrix, and A is said to be unitary if A star is equal to A star A is equal to I n, that is the n cross n identity matrix. It follows from the definition and the above theorem that T is unitary respectively orthogonal operator if and only if the matrix representation TB is a unitary respectively orthogonal matrix. The proposition says that A is unitary if and only if the columns as well as the rows of A form an orthonormal basis for the inner product space Fn with respect to the usual inner product. The proof is simple and it follows from I is equal to A star A is equal to A star. We have learned definitions of orthogonal and unitary operators, and also we have proved a very important theorem which gives a set of equivalent conditions, and each one can be used as a definition of a unitary operator. And we could define orthogonal and unitary matrices. Now it is time to again go back to normal and self-adjoint operators. We have learnt that they are diagonalizable. In fact, what we had proved was that there exist orthonormal basis of eigenvectors such that the operators are diagonalizable. Now with the help of unitary and orthogonal matrices, we can say it more precisely in the matrix form, and we will introduce the names called orthogonally diagonalizable and unitarily diagonalizable. In our discussion on normal and self-adjoint operators, which we did in chapter 5, module 5, we proved diagonalization of complex normal or real self-adjoint operators. Now we can restate those theorems in matrix form. Theorem: let A be an n cross n matrix over F if A is complex normal respectively real symmetric matrix, then there exists an orthonormal basis B for Fn consisting of eigenvectors of A. Therefore, A is similar to a diagonal matrix D, and A can be written as Q D Q inverse such that Q is unitary respectively orthogonal matrix. Definition: we say that A is unitarily diagonalizable respectively orthogonally diagonalizable if A can be written as Q D Q inverse such that Q is unitary respectively orthogonal and D is diagonal. In terms of this newly introduced terminology, we can restate the diagonalization of complex normal and real symmetric matrices as follows. Complex normal matrices are unitarily diagonalizable and real symmetric matrices are orthogonally diagonalizable. We will have the opportunity to use this theorem extensively when we study symmetric bilinear forms. Let us first understand this theorem with the help of some examples. A is the 3 cross 3 real symmetric matrix given by 1 0 1 in the first row, 0 1 0 in the second row and 1 0 1 in the third row. this is diagonalizable, in fact orthogonally diagonalizable, and the set consisting of the vectors 1 over root 2 times 1 0 minus 1, then 0 1 0 and 1 over root 2 times 1 0 1 is an orthonormal basis of eigenvectors of A. We therefore have A is equal to Q D Q inverse such that D is the diagonal matrix where the principal diagonal entries are the eigenvalues of A, and Q is this matrix whose first row is 1 over root 2 0 1 over root 2, second row is 0 1 0 and the third row is minus 1 over root 2 0 1 over root 2. And this orthogonal matrix Q is in fact the basis change matrix. Well, why is it orthogonal? That is because the columns of this matrix are nothing but the vectors in that orthonormal basis, and therefore Q is an orthogonal matrix. The example, A is this real symmetric matrix whose first row is 4 2 2, second row is 2 4 2 and the third row is 2 2 4. The matrix A is symmetric and hence orthogonally diagonalizable. This set consisting of the vectors 1 over root 2 times minus 1 1 0, then 1 over root 6 times 1 1 minus 2 and 1 over root 3 times 1 1 1 is an orthonormal basis consisting of eigenvectors of A. Therefore, the matrix A is Q D Q inverse, where D is this diagonal matrix with principal diagonal entries 2 to 8 which are the eigenvalues of A, and Q is this 3 cross 3 matrix where the first row is minus 1 by root 2, 1 by root 6, 1 by root 3, the second row is 1 by root 2, 1 by root 6, 1 by root 3 and the third row is 0, minus 2 by root 6, 1 by root 3. Q is orthogonal, in fact the basis change matrix. And why is Q orthogonal? Because the columns are precisely the vectors appearing in that orthonormal basis. Example, the matrix A, which is a 2 cross 2 matrix, first row is 5 2 and second row is 2 2. This is again real symmetric and hence orthogonally diagonalizable over R. We find an orthogonal matrix Q such that A is Q D Q inverse. The eigenvalues of A are 6 and 1 with eigenvectors V1 that is equal to 2 over root 5 comma 1 over root 5 and V2 that is 1 over root 5 comma minus 2 by root 5 respectively. Now, the set containing V1 V2 is an orthonormal basis for R2 and therefore the diagonal matrix D is 6 0 0 1. You can see the eigenvalues 6 and 1 appearing on the principal diagonal, and the basis change matrix, which is an orthogonal matrix, is given by Q, that is 2 by root 5, 1 by root 5 in the first row and 1 by root 5 minus 2 by root 5 in the second row. Once again, Q is orthogonal because the columns of Q are precisely the vectors appearing in the orthonormal basis for R2. One more example, a 3 cross 3 real symmetric matrix given by 2 3 0 in the first row, 3 5 minus 1 in the second row and 0 minus 1 2 in the third row. This is orthogonally diagonalizable over R. To find an orthogonal matrix Q, such that A is equal to Q D Q inverse, we see that the eigenvalues of A are 2, 7 and 0, and the corresponding eigenvectors are V1 is equal to 1 by root 10, comma 0, comma 3 by root 10, V2 is equal to 3 by square root of 35, comma 5 by square root of 35, comma minus 1 by square root of 35, and V3 is equal to minus 3 by square root of 14, comma 2 by square root of 14, comma 1 by square root of 14. Now, these three vectors form an orthonormal basis for R3, and therefore, the diagonal matrix D is given by 2 0 0 in the first row, 0 7 0 in the second row and 0 0 0 in the third row. The eigenvalues 2, 7 and 0 are appearing on the principal diagonal, and Q, that is 1 by root 10, 3 by root 35, minus 3 by root 14 in the first row, 0, 5 by root 35, 2 by root 14 in the second row, and 3 by root 10 minus 1 by root 35, 1 by root 14 in the third row, is the basis change matrix, which is again orthogonal, because if you look at the columns, you will see that these are nothing but the vectors in the orthonormal basis. We have learned normal, self-adjoint, and then unitary and orthogonal operators on finite dimensional inner product spaces. First, we started with Schur's theorem and proved, under the assumption that the characteristic polynomial splits in the base field, that the operator can be put in the upper triangular form. And then we proved that if the base field is C and the operator is normal, then it is unitarily diagonalizable, and if the base field is R and the operator is self-adjoint, then it is orthogonally diagonalizable. So, unitary and orthogonal operators, rather matrices, appear as the basis change matrices when we are talking about diagonalization of normal and self-adjoint operators. Now, we will see orthogonal operators more closely, especially from the perspective of geometry.